Lua guided missiles. Alright, so what do I need to code a Lua guided missile? First up, let's make sure our missiles are set up correctly. They need a Lua receiver. They need a Lua transmitter on every launch pad. We need general processing power. And to get the amount, you'll look at the missile, go to the Q menu, and under general processing power used, you'll see the number. That number is 9 for large missiles, and that means I need 9 general processing power cards per missile in the air at any time. So if I have 3 missiles, I need 9 times 3 general processing power cards. Lastly, I need a Lua box. Now the Lua box you'll find under the Control tab in the Build menu under Lua box. And you can place this anywhere on the vehicle, and this will control our Lua receivers through the code inside the box. Lastly, I want to make sure that everyone knows that this does rely, just like with remote guidance systems, an accurate detection system on the vehicle. So for testing purposes, I'm going to go to the Options Config menu and set my accuracy to 100% and override. That way I know in testing if the missiles aren't working correctly, it's not because the detection system, it's due to the code. Alright, so let's jump into the Lua box. And if you're familiar with Lua coding, you'll know what the update function is. This is just running 40 times a second, and it contains one argument, which is the instance object of the game, which contains functions for getting variables and setting variables. So this is helpful because in this case we want to set an aim point for the missiles. And that function, this is going to be the function that pretty much everything is based off of in this code, is the set Lua controlled missile aim point. This argument will, once we once we give it the arguments that it requires, will set the missile that you're telling it to the point that you want it to go. But it does contain a number of arguments, and to explain what those arguments are, I need to explain indices. So every vehicle has a number of transmitters, Lua transmitters, and from 0 to whatever number. And in this case we have 3, so I have indexes of, and all indexes start at 0, so I have 3 transmitters. Index first is 0, and then 1, and then 2. And then every transmitter has a number of missiles. So missiles have their own index. So if the transmitter has an index of 0, then its missiles it control will have their indexes starting at 0. So the first missile launched from this transmitter has index of 0. The second one has an index of 1, and so on. Once a missile's destroyed, the indexes drop back down to the lower numbers. So if my first missile's destroyed before the next missile's launched, the next missile's index is 0. If I have 2 missiles in the air and one is destroyed, the index of 0 was destroyed, the index at 1 actually goes back down to 0. So it's always starting at 0 and going up for every missile that it controls. So in order to control each missile individually, I need to know these indices. And that's why this has 2 arguments for indices. One is, what's the transmitter index? So which transmitter am I trying to send the information to? And then which missile from that transmitter? So we'll do index of M for missile. Then I need, the last arguments are the coordinates. Where do I want to aim that missile? So we get the coordinates point, and we need the X, Y, and Z coordinates of it. So in order to go through every missile, because this code will assign each missile individually, I need to loop through each one that exists. And because indices start at 0, I know my first transmitter will be 0, and then I'm going to go up to how many transmitters are there on the vehicle, which I can get a count of using just get Lua transceiver count. And of course, count is going to give me a count, and indices start at 0, so I know that it's actually the count minus 1 is the largest indice that I want to go up to. So I do minus 1. And then I need to do this for every missile. So I can get the count of missile using get Lua controlled missile count, and then from that transmitter, so I need to know which transmitter I'm counting the number of missiles. And then of course, like before, indices start at 0 and the counts don't, so I need to minus 1. So now I'm looping through every missile, and I'm going to set its aim point individually, and then I'm going to end these statements, these for loops. So essentially what I have now is looping through every missile that exists, aim it at point. I don't have point yet, so I do have to figure out what do I want to point them at. I can pick numbers, or I can get something that's actually useful. In this case, the target position is a useful point to aim at, and that is just we'll say target position is just a function that we can get from our mainframe's point. So if I get target info, so the target is what my mainframe is pointing at. Which mainframe, because there are going to be more than one, so I'll do 0 for the first mainframe, and 0 is the primary target. Aim point position. Now this is the position where that mainframe is pointing. So now target position is giving us a point to aim at. And we can test this and make sure this is working. Let's just set point equal to, so point is where our missile, it's a 3D vector, right? So it's actually a point in a 3D space. So point, and then target position is giving us a point in 3D space. So target position is where we want to point our missile. So it's just literally just pointing at the target. Send the missile to that target. If I launch this, we can test it and see if it works. It should work like any other missile does now without any predictive guidance. Just go to where the target is. You can see it's working just like any other missile does. In fact, I can test it alongside a remote guidance missile with nothing but the remote's guidance unit in it. So we'll launch them here at the same time, and we'll see if there's any difference in how they work. They should work exactly the same. There we go. So if we see the missiles coming out here and compare them, they're all doing exactly the same. Aim towards the target, and if the target moves, we'll aim towards the new location of that target. And you can't even tell the difference between which missile was Lua and which one is remote guidance built in. But we haven't gained anything here, right? You're saying, well, why is Lua better if it's doing the same thing as remote guidance? But I just spent all this materials on a Lua transmitter, or the Lua receiver and the Lua transmitter and a Lua box, which they cost 100 each. This costs 90. So we haven't really gained anything here. But if you notice, remote guidance doesn't have any other predictive abilities. You do have to add that in using up a module. And yes, an extra module does take away some of the payload capacity, and you can use some of the internal free space to add that back, but you still lose some, right? You're still losing some of your payload capacity or fuel capacity, whatever you want to take out in order to fit a predictive guidance module in. But with Lua, you don't need to change anything. The Lua receiver is all coded now from the Lua box. So if we want to add guidance in, we're not losing any payload capacity or any fuel capacity. We can add an extra pair of fins. So this becomes the benefit of a Lua-coded missile. So let's try now to code a missile to predict where the target is going. Let's try to intercept and act. Let's build basically a predictive guidance missile. And in order to do that, I need a couple of more. I need to get a couple more things before I start telling the missile where to go. I'm gonna need. We're gonna need the target position still, but we need to know where the target's going. So we need a velocity vector. So the target. Let's do target velocity. And this is the same, get target info 0, 0, but this will just be velocity. So now I know where the target's going. I have a velocity vector, which is the magnitude of its velocity, which is just its speed, and then I have a direction. That'll tell me, all right, now I need to go in that direction because that's where the target's moving. But I need to know how much in that direction do I need to go. And in order to do that, I need to know the distance and time it'll take for my missile to close that gap. So let's change point now. And instead, we need the following information. We need, because like I said, we're trying to get to what's the distance from the missile to the target and how long will it take me to close that gap. So I do need the missile's position. And that's going to be get Lua controlled missile info. And I need the indices of the missile position. And then I need to know, from that, I can get the distance. I can just subtract target position from missile position. But I'm also going to need to know how fast is the missile going. And then I'll know how long it's going to take for the missile to get there. So I need missile speed. And in this case, I can get that from get Lua controlled missile info. But this time I want the velocity. And because that gives me a vector and I just want the speed, I'm going to take that and do a vector3 function. And this is just magnitude. That'll return the magnitude of the vector, which is the speed. And then I need target distance. And that is going to be, well, let's see. I need you can use a vector3 for this. And just give it 2 points. So vector3 distance will give you the distance between 2 points. And I just want target position and missile position. So that gives me my distance to my target, and I have a missile speed. Now I should be able to predict some kind of a prediction of where that target's going to be by the time I get there. And I know how long it's going to take for me to get there. So let's say prediction is equal to target velocity times target distance divided by how long. So basically divided by my missile speed. So what I'm doing here is I'm taking the velocity of my target, and then how long it takes to get there is a function of distance divided by speed. And that'll give me a vector. So now this is a target velocity is a vector, and I'm multiplying it by a scalar, which is going to give me the vector. And that vector is the magnitude and direction that we're going to predict that target will move in the time it takes me to get there. And then I'm just going to do point to be the target position like before, but now I'm going to add in that prediction, which is, like I said, where it's going to move in the time it takes me to get there. If I save this, hopefully it'll work. Now what our missiles are doing is it's looking, okay, I'm looking ahead and I'm basing it off my current speed and my distance and the velocity vector of the enemy. Where am I going to intercept it? But we run into a problem. So if anyone's figured out why this is happening, right, congratulations. But I can explain that by talking a little bit more about vectors. So the speed that our missile is moving relative to the target is different than the speed of the missile. So how long it's going to take to close the gap to the target is different than just taking the distance and dividing it by the missile speed. And that's because the target is moving either with or against my missile's speed. So I actually need to look at my target's velocity and see if I'm adding distance because of that prediction. So one way to do this is you could do an iterative approach where we look at this new point and then we say, all right, now the new prediction is that point divided by the distance to that point divided by the missile speed. And that will give you a better prediction. But another way to do it is to find the relative speed. So what is the speed of my missile relative to the speed of the target moving in the same vector as the missile to the target? So basically, is it moving away or towards me, or is it moving to the side? If it's moving to the side, I don't care. It's not adding any distance, not much anyway. So in order to do a relative speed, I need to know the vector to the target, and then I'm gonna take, so that vector is the direction from my missile to the target, and then compare that to the target's velocity in that direction of that vector. So the vector to the target is going to be a target, so target position minus missile position. And this is giving me a vector pointing from the missile to the target. But I actually want to normalize this, and I'll explain why. So vector 3 dot normalize will take a vector and bring it into a unit vector, which is, if you take the squared sum of the squares, you get 1, which is just the magnitude, basically. So the magnitude of this vector is 1. And the reason why I want that is because when I compare the velocity vector up here of that target to the vector to the target, I want to know how much of this velocity is in the direction of this vector. And that's a really simple linear algebra equation called the dot product. So let's do something called relative speed. And now what this is going to be is our current missile speed. And we want to subtract how much of the target speed is going with the missile speed. So if the target is going in the same direction as the missile is trying to go, then we know we have to subtract from our missile speed, and then our prediction will have a more accurate relative speed. So it's missile speed minus, and how do we get how much the target velocity vector is moving in the vector that the target is? It's, like I said, the vector 3 dot product of our target vector, which is a unit vector. And when you do a unit vector with a velocity vector, you get velocity in the direction of that vector. So target velocity, and this will give us now the speed of our missile relative to the speed of the vehicle in the direction. Basically what it is missile speed, and then minus the speed of the target in the direction that we wanted to go. So with relative speed now, we know we can take our prediction, and instead of dividing by missile speed, we'll divide by relative speed. And in this case, I think everything should work. Let's give it a shot and see how we do. So if the vehicle is moving, you can see that the vehicle is actually moving closer or towards the missile, and in that case we're actually going faster. Relative speed is actually faster than the actual speed of the missile, and that will help determine a better intercept point. We are not taking into consideration yet the acceleration of the vehicle, so it is accelerating slightly in a circle, meaning it's turning, but it's not enough to throw off the accuracy of this prediction. So that's all you need to do for a predictive guidance missile. And now we're getting predictive guidance that actually is better than a remote guidance with a predictive guidance module installed. So we can test that here. So a predictive guidance with a module on the left versus a Lua coded on the right when they launch. Here we go. So the arc of the predictive guidance, you can see a straight line means a better prediction. So these are arced, and the Lua guided are straight lines, meaning they've done a little bit better job of predicting where the intercept's going to be. They didn't have to correct. And then now we've actually gained something from having Lua coded, because now with one module, we're able to do what any other missile can do with two, and even do it better. So now, if you wanted to end here and use this code, this would be like a great spot to. I think in my comments I'll add in this code. We'll end the video here as part 1, and then part 2 I'll continue with more advanced stuff. We'll start off with maybe something like a missile that goes to the enemy but just circles them, like for radar buoys. We'll do something water skimmers, and some that go up into the air and come down like artillery. But we'll cover that in the next part 2 of this. And from here, I think we have a really good code that you can use. Like I said, I'll put the code in the comments. So I'll see you in the next video. Thank you.